Group 9, also known as the statisticians, includes Yawling Leo, Preston Starkey, David Olatunji, and Claire Lakin. We are in the summer 2020 semester of the University of Arkansas's Engineering Probability and Statistics class, and our professor is Dr. Beam. In our presentation, we will be covering an explanation of the experiment, the lab equipment used, the experimental design, the analysis parameters, the results of the experiment, and the conclusions we made. We did an impact craters experiment during which we dropped a ball into a shallow container of flour while varying different factors. Our response variable was the diameter of the crater produced in the flour, and it was measured in centimeters. Our three factors were weight measured in grams, drop height measured in inches, and drop angle measured in degrees. The lab equipment required for the experiment is as follows: flour, a container for the flour in which the ball lands, a yardstick to measure the height of the drop, a ruler to measure the diameter of the crater, 2 balls, one of which is 30 grams and the other is 100 grams, a small scale used to weigh the balls, a ramp down which the balls fall at an angle, and finally a protractor to measure the angle of the drop. As far as the design of our experiment goes, we assigned 2 levels, high and low, to each of our factors. For weight, the low level was 30 grams and the high level was 100 grams. For drop height, the low level was 15 inches and the high level was 30 inches. For drop angle, the low level was 30 degrees and the high level was 90 degrees. And these levels and factors produced a 2 to the third design, and we had 4 replications. Experiment runs 8 through 11 went as follows.
As a group, we collectively decided to use an alpha of 0.05, and from there, to determine the significant factors, we looked at the p-values for each of our factors and interactions and determined whether it was over or under 0.05. So we ran the ANOVA, and as you can see, the only factors that were significant and below 0.05 were the drop height and the interaction between drop height and drop angle.
All 3 of these scatter plots look good. The first one on the far left has a point at 100 grams that looks like it's a little bit far away from the rest of the data, but most of these points cluster around their respective means. The most significant factors are the drop height with a standardized effect of 0.5 and the interaction between drop height and drop angle with a standardized effect of 0.61.
Using only the significant factors of the drop height and the interaction of drop height and drop angle, we were able to recreate the ANOVA table as well as create the regression equation, which is the crater diameter equals 7.66 plus 0.25 multiplied by the drop height plus 0.3063 multiplied by the interaction of drop height and drop angle. Using this equation, we found that the crater diameter will be greatest with a 100-gram ball, a drop height of 30 inches, and a drop angle of 90 degrees. So, for instance, if we had a ball weight of 100 grams, a drop height of 30 inches, and a drop angle of 30 degrees, the crater diameter would be 7.66 plus 0.25 times 1 plus 0.3063 multiplied by 1 multiplied by -1, which would give us 7.6037 centimeters. Looking at both the normal plot of residuals and Cook's distance graphs, our data does show normality. With the normal plot of residuals, it looks like it does pass the fat pencil test. And with the Cook's distance graph, there are no data points that exceed the red horizontal line. So they both together show that our data is normal.
We got our greatest crater diameter from a drop height of 30 inches and a drop angle of 90 degrees. In conclusion, the 2 most significant factors were the drop height and the interaction between drop height and drop angle. In summary, the greater the vertical distance between an object and a bowl of flour, and the more direct an object is thrown on top of that flour, the greater the crater diameter would be. We also concluded that there is no such thing as over-communication in a group project. Great leadership leads to great productivity, collaboration, and results. Designing experiments can be a simple process with adequate knowledge and adequate software. And finally, consistency in the testing environment along with randomized tests are very important in design of experiments.